Here we go. Constant multiple rule. I tried to be careful in the previous example to have just x raised to a power, not 5x raised to a power or 3x raised to a power, as I almost did. Constant multiple rule, and I'll go with both this and the example. If f is a differentiable function at x and c is any real number, then if you form a new function by taking f of x and multiplying it by a constant, you can imagine what it does to the graph. You know, it just stretches the graph. Stretching the graph vertically is not going to alter its differentiability. If there wasn't previously a corner, there's not going to be a corner by just stretching it vertically. And if there wasn't previously a vertical tangent line, just stretching it by multiplying by c is not going to cause there to be one. So CF is going to be differentiable, and we can obtain the derivative by taking the derivative of f and multiplying it by c. Basically, the derivative of a constant times a function is equal to that constant times the derivative of the function. Another way of looking at it is the constant basically can be passed through, or up and over as I've drawn it there, the derivative. You can pass the constant through the derivative. You can't pull an x out of there, but if the constant does not depend on x, you can pass it through there. So in this case, if we could find the derivative of x to the negative 7th power, and we multiply that by 3, then that would be the derivative of 3x to the negative 7th. So I'm going to do this in gory detail for the 3x to the negative 7th, and then at some point someone will suggest, rightly so, why not just multiply the negative 7 by the 3? And of course, in practice, after this example 3a, that's what we'll do from that point forward. But I feel like I need to show it without doing that first. So to find the derivative of this, I've got y here instead of f of x. I'm trying to mix it up so you're comfortable with different notation. F prime of x in one example, dy dx in another example. So it doesn't leave you wondering, what does he mean by that? Well, in both cases, I mean, find the derivative. Dy dx equals, let's say it like this, ddx of 3x to the negative 7 using the constant multiple rule. The 3 comes outside, so it's 3 times ddx of x to the negative 7. So we find the derivative. I guess it'll take a couple of steps to find the derivative of x to the negative 7. This is 3 times negative 7 x to the negative 8. And now with the ddx gone at any time, we feel like multiplying by 3. Of course we can. This equals negative 21 x to the negative 8, which then we could write as negative 21 over x to the 8th. Now, if we were to do a few of these, I'm just going to do one and make this observation. You can see that if we just take the negative 7 and multiply it by the 3, we get the negative 21, and then reduce the exponent by 1. So long as you know that we're applying the constant multiple rule to enable us to do that, it's fine. We can do this every single time. Multiply that exponent by the coefficient, and then we don't have to include these extra steps in the middle. So I'm going to go ahead and do that with the b part, dy dx. If we multiply the 4 by negative 8, negative 32, reduce the exponent, and we get x cubed, yes. And the next one, let's see, probably want to work on that a little bit. Y equals 5/3 x to the 1/2. So dy dx equals 1/2 times 5/3 x to the negative 1/2. Subtract 1 from the exponent. And so dy dx, can I do 2 or 3 things at once? Yeah. A lot going on here. Probably I should say 5/6 x to the negative 1/2, and then say that's 5 over 6x to the positive 1/2. And while I'm at it, 5 over 6 times the square root of x. This would give us an expression for the derivative of this function.